Okay, so welcome to the Tutte Colloquia, and we're very happy to have Tom Kelly here. Tom graduated from our department about 2 years ago, and since then he has been working in University of Birmingham. Keep working on graph theory. So today he's going to talk about some new development in the Erdős Faber Lovász conjecture. Welcome.
Thanks, Jane. Thanks for the opportunity to speak. It's great to see all these familiar faces. So I'm going to talk about the Erdős Faber Lovász conjecture. All this is joint work with Donggyip Kang, Daniela Kuhn, Abhishek Mapuku, and Derek Ossis, and all of us are at the University of Birmingham. Okay, so the Erdős Faber Lovász conjecture is a question about edge coloring hypergraphs. But before we get there, I want to start with some basic notions. In particular, let's just start with graphs. So a matching in a graph is just a set of disjoint edges, and a proper edge coloring of a graph is an assignment of colors to the edges so that no two edges of the same color share a vertex. Here I have the Peterson graph, and I've given you an example of a proper edge coloring. So you can check that it is indeed proper. In particular, the color classes all form matchings. So the connection between matchings and edge colorings here is that edge coloring is like a decomposition into matchings. In general, it's interesting to find large matchings or edge colorings that use a small number of colors. And so the chromatic index is a useful notion for that. It's the minimum number of colors that you need in a proper edge coloring of a graph, and it's denoted by chi prime. So I've exhibited to you this proper edge coloring of the Peterson graph using at most 4 colors. And so in particular, its chromatic index is at most 4. And it's equal to 4 because the Peterson graph quite famously does not have a proper edge coloring with 3 colors. So if you haven't seen a proof of that, I recommend you to think about it. I'm sure a lot of you are familiar with these definitions, and also these results, but I hope you'll appreciate the representation of the Waterloo formal faculty here. The study of matchings and edge coloring is really quite classical in graph theory, going all the way back to Hall from 1935, which characterizes when a bipartite graph is a perfect matching. Touch theorem characterizes in general when a graph is a perfect matching. And a perfect matching is a matching that covers all the vertices, so kind of as large as it could possibly be. And Edmonds' Blossom algorithm is a polynomial time algorithm for finding a maximum matching in a graph. On the coloring side of things, Vissing's theorem says that the chromatic index of every graph is always one of 2 values. It's either the maximum degree or it's the maximum degree plus 1. So the degree of a vertex is the number of edges that contain it. So for example, in the Peterson graph, every vertex has degree 3. And so clearly you need at least 3 colors to color the Peterson graph. And so the non-trivial part of Vissing's theorem is that the chromatic index is at most the maximum degree plus 1. So yeah, these are very fundamental results in graph theory. In fact, in my comprehensive exam that I had to do at Waterloo in 2016, I had to prove Vissing's theorem. And I also had to use Tutt's theorem to prove Peterson's theorem. So quite classical stuff. In the paper that I'm talking about, we actually use Hall's theorem, Tutt's theorem, and Vissing's theorem. But the main reason that I'm bringing this up is to kind of contrast the setting of graph theory, where this type of stuff is very well understood, with the setting of hypergraphs, where things are a lot more complicated. So in hypergraphs, edges can have any size, whereas in graphs, every edge has size 2. So here's an example of a hypergraph, and all of the edges have size 3. So throughout the talk, I'll have lots of pictures of hypergraphs, and I'll be drawing edges like by wrapping a line around the vertices of the edge. So this triangle is an edge of size 3, as is this one. the notions of matching and coloring and chromatic index, they all carry over to the hypergraph setting. So this is these two blue edges are matching. Same with these red and green edges. And so combining them, you get a proper edge coloring of this hypergraph with the most 3 colors, so the chromatic index is 3. But like I said, for matchings in hypergraphs in general, things are a lot more complicated. For example, the problem of finding a maximum matching in hypergraphs where all of the edges have size 3 is actually one of Karp's original NP-complete problems. So that is to say that we don't expect that there's some kind of generalization of Edmonds' Bossum algorithm to work for hypergraphs in general. Another illustrative example is the question of the existence of block designs or Steiner systems with particular parameters. The definition of that is not so important. What matters is that they correspond to perfect matchings in a particularly highly symmetric hypergraph. And the question of whether they exist for particular parameters was originally posed in the 1800s, and it was open for over 100 years until it was recently resolved in the last decade by Kivash. And really that's quite a tour de force of a proof. So in other words, we wouldn't expect, for example, that there's a generalization of touch theorem for hypergraphs unless you think that this problem is not quite as hard as it seems, because you would just apply that theorem to these hypergraphs. That's the story with matchings, and for edge colorings, that's like a decomposition of a hypergraph into matchings, which is in some informal sense an even more difficult problem. Nevertheless, for Vissing's theorem, there might actually be some kind of generalization in the setting of hypergraphs, and that's kind of a way to think about the Erdős-Faber-Lovász conjecture. So here's the conjecture. It's quite easy to state. You just need one more definition, that of a linear hypergraph, which is one where every pair of vertices is contained in at most one edge. So hypergraphs in general can be quite wild. They can have an exponential number of edges, but the linear hypothesis really tames these graphs. In particular, they're kind of more graph-like. Hypergraphs are more graph-like when they're linear. So the conjecture states that, quite simply, every n-vertex linear hypergraph has chromatic index at most n. Well, I think this quote of Erdős is quite appropriate in relation to this conjecture. It says that an innocent-looking problem often gives no hint as to its true nature. It might be like a marshmallow, serving as a tasty tidbit, supplying a few moments of fleeting enjoyment, or it might be like an acorn, requiring deep and subtle new insights from which a mighty oak can develop. The reason I think it's appropriate is because at first glance, the Erdős-Faber-Lovász conjecture might seem a lot more like a marshmallow, but in fact, I think it's more like an acorn. And I hope that by the end of the talk, you will agree with me on that. I think Erdős, Faber, and Lovász themselves also thought that this problem would be a marshmallow when they first thought of it. The story goes that when Erdős and Lovász were visiting Colorado, where Faber was a young professor in 1972, they were talking at a tea party and they came up with this conjecture. And they thought that it would be easy to prove, so they agreed to meet the very next day to write down a proof. And then clearly that didn't happen, or else I wouldn't be here talking to you about it today. Erdős often wrote about this problem throughout the years, and he would say that it's one of his 3 favorite problems. Erdős was kind of famous for not just solving lots of problems in combinatorics, but also opposing them. And he really had an incredible ability, I think, to come up with acorn-like problems. And for problems that he particularly liked, he would often offer a cash reward, like a very small cash prize. So for this one, after he realized the difficulty of it, he offered $50 for a solution that he eventually raised to $500. And there's only a handful of problems that Erdős offered more money for, but he quite liked this one. One of the reasons that I think it's so interesting is because of the nature of the extremal examples. There's kind of 3 different families of extremal examples for this conjecture. The first family I have on the left is the projective planes, the finite projective planes. This example here is the Fano. I'm sure y'all have seen it before. It's the projective plane of order K, projective plane of order 2. In general, the projective plane of order K is a K+1 uniform hypergraph, which means that the edges have size K+1. And it's linear, and it has n vertices and n edges, where n is equal to k squared plus k+1. The reason that it's extremal for the EFL conjecture, which is to say that it has chromatic index n, is that it's intersecting. So a hypergraph is intersecting if every pair of edges intersects at a vertex. And in order to color an intersecting hypergraph properly, you need to assign every edge distinct colors. So for the Fano, it's got 7 edges, and I needed 7 edges to color it here. A similar example is the degenerate plane, also called the near pencil, which I've drawn here in the middle. And this one is extremal for the same reasons as the projective plane. It's intersecting and it has n edges, but it's a bit more of a trivial construction. So the construction is to take a special vertex and add a size 2 edge containing that vertex and for every other vertex in the hypergraph. And then to add one remaining size n-1 hyperedge to swoop up all the other vertices. And you can see that it's intersecting in linear with n edges. Both of these examples, the projective plane and the degenerate plane, are coming from some kind of geometric thing, some kind of point line configuration where the points are the vertices and the lines are hyperedges. So and they satisfy some geometric axioms. So for example, every pair of points is contained in a line, a unique line, and that's the condition of linearity. And every pair of lines intersects in a vertex, and that's the condition of being intersecting. One important thing I want to point out about these two examples is that as n tends to infinity, the size of the edges also tends to infinity. So the projective plane has edge sizes roughly square root n, and the degenerate plane has this one huge edge. The last extremal example is the complete graph when n is odd. And this one is quite different. The edges have size 2 because it's a graph. So the complete graph is one in which all of the edges are present. To say that it's extremal, suppose, well, for a contradiction that there's an edge coloring that uses fewer than n colors. Since every vertex has degree n-1, every vertex will see an edge of every color, which in particular implies that every color class is a perfect matching. So that's not possible when n is odd. So you get a contradiction. Okay. Another interesting feature of the Erdős-Faber-Lovász conjecture is that there's several different ways to formulate it that are in fact equivalent, but are at first glance quite different. And here's one such example. It's as follows. Take a hypergraph that is n uniform and has n edges, but is still linear. And the conjecture is that you can color the vertices of H with at most n colors in such a way that every edge contains a vertex of every color. And so to see why this is equivalent, I need to explain to you the notion of hypergraph duality. So I'll do this with an example. So consider this hypergraph on the left, consisting of this size 3 edge and the remaining edges of size 2. Take the dual. The dual is a hypergraph where its vertices are edges of the original. And so it's actually easier to see with colors. So for example, this blue triangle at the top will correspond to this blue vertex in the dual. And this bottom blue edge will correspond to this bottom blue vertex. And vertices of the original hypergraph correspond to edges of the dual. So for example, this bottom left vertex that has degree 4 will correspond to this size 4 hyperedge. And you can check that, well, for one thing, this is a dual operator, so applying it twice, you get the original. And also that linearity is preserved. So this is a linear hypergraph, as is its dual, and that holds more generally. And so since the EFL conjecture is about proper edge coloring, if we consider the dual of these graphs, rather than coloring the edges, it becomes a question about coloring the vertices. And the condition about being proper is equivalent to that of saying that each hyperedge does not contain two vertices of the same color. So with this notion in hand, you can kind of see how this dual formulation of the Erdős Faber Lovász conjecture is equivalent. There's still some technicalities involving edges of size 1, but basically the n vertices from the original conjecture become n edges. Linearity is the same, and I'm coloring the vertices instead of edges, as is the case when you take the dual. For this one, to state this version of the conjecture, you don't really need the notion of hypergraphs at all. You can just basically use set theory. So for example, just a direct translation of this is that if you have n sets of size n that pairwise have intersection at most 1, then their union can be colored with n colors so that every color appears in each of the sets, which might look quite different from the original EFL conjecture and also quite marshmallow-like, but it is indeed equivalent. Okay, so one more equivalent version is the following. If you have a graph that's the union of n complete graphs, each having at most n vertices, such that every pair shares at most a vertex, then the chromatic number is at most n. I didn't define the chromatic number, but it's kind of analogous to the chromatic index, but for vertex coloring. The way that you get this conjecture is by considering the line graph of the original hypergraph. So for example, the line graph of this hypergraph on the left is this thing on the right, and it's similar to the dual in that the edges of the original become vertices of the line graph. So that you can see the line graph has the same set of vertices as the dual. And a quick way to describe the construction is that you take the dual and you replace each hyperedge with a complete graph. And so those complete graphs correspond to the hyperedge in the dual formulation. Perhaps the more familiar way to define it is that edges in the original graph that share a vertex become adjacent in the dual. And yeah, proper edge coloring corresponds to proper vertex coloring. And so that's how you go from the chromatic index to the chromatic number in the conjecture. Okay. Now let me tell you about some previous results for the conjecture. So for the rest of the talk, I'm going to mainly work with the original formulation that I gave you about edge coloring linear hypergraphs. A direct approach that you could take is to try to just find the best bound on the chromatic index that you can. And something that you can show fairly trivially is that the chromatic index is at most 2n minus 3. So at most a factor of 2 away from what the conjecture is. By considering, well, by first ordering the edges by their size and then coloring greedily. And this is actually going to be useful for us later. So it'll come up later in the talk. But Chang and Waller in '89 kind of improved upon this argument a bit to get that you have a bound on the chromatic index of 3n/2. Another approach to the conjecture would be to prove relaxations of it, where you replace the chromatic index with something different. So actually predating the conjecture, De Bruyne and Erdős in 1948, they proved something that's essentially equivalent to saying that the EFL conjecture is true for hypergraphs that are intersecting. And in other words, the clique number of the line graph is at most n, and the clique number of the line graph is at most the chromatic index. Seymour proved a strengthening of this result by showing that every n-vertex linear hypergraph has a matching of size, at least the number of edges divided by the number of vertices. The reason that this is a relaxation of the Erdős Faber Lovász conjecture is because if the EFL conjecture is true and you take a edge coloring with n colors, then the average size of a color class is this quantity. So in particular, the largest color class is a matching of size at least this. And this actually strengthens the De Bruijn-Erdős theorem, because if you have a hypergraph with more than n edges, then Seymour's theorem tells you that it has a matching of size bigger than 1. So in particular, it's not intersecting. And then 10 years later, Kahn and Seymour generalized the Seymour's result to the fractional chromatic index. So the most important results for this conjecture, I think, have been proved using a probabilistic approach. One such result was proved by Faber and Harris quite recently, actually, and that they showed that the conjecture is true if all of the edges have size at least 3 and size at most some absolute constant times the square root n. And an important thing to note about this result is that this hypothesis on the edge sizes is excluding all 3 of the extremal examples. So if you recall, I told you the projective plane has edges of size root n, and the degenerate plane has a very large edge of size n-1, and the complete graph has edges of size 2. So none of these fit into this hypothesis. But back in 1992, Kahn proved that the chromatic index of every n-vertex linear hypergraph tends to n as n tends to infinity. And actually, Erdős gave him a consolation prize of $100 for this. Both of these results are proved using a generalization of the Pippinger-Spencer theorem, which says that a linear hypergraph with bounded edge sizes and maximum degree of delta has chromatic index that tends to delta, as delta tends to infinity. This Pippinger-Spencer theorem already implies something quite non-trivial about the EFL conjecture. In particular, it implies a relaxation of the Faber-Harris conjecture, where if the edges have size at least 3, but size at most some constant, then if n is large, then you can color the graph with the most n colors. And the reason for this is that this condition that the edges have size at least 3, combined with the linearity hypothesis, imply that the maximum degree is at most n over 2. And for a similar reason, the Pippinger-Spencer theorem implies the weaker version of Kahn's result, where the edges have bounded size, because in general, a linear hypergraph has maximum degree at most n. And so the way that these two results are proved is by first starting with the large edges, coloring them, and then using this kind of list coloring version of the Pippinger-Spencer theorem to extend the coloring to the small edges. Okay, so now I can tell you about where we come into the picture. The main result that I want to tell you about today is that we can prove the conjecture for all but finitely many hypergraphs. So in particular, if n is sufficiently large, every n-vertex linear hypergraph has chromatic index at most n. We can also prove a stability result that Kahn predicted. It says that if you have a hypergraph that's linear and has n vertices, and the maximum degree is bounded away from n, and the number of edges of size roughly square root n is also bounded away from n, then the chromatic index is bounded away from n by sigma n. So the reason that this is a stability result is that these two conditions together imply that the hypergraph is not too close to being one of the extremal examples. In particular, the first bullet point excludes the case of the degenerate plane and the case of the complete graph, because both of these have vertices of degree n-1. And the second bullet point, which maybe is a bit more interesting, excludes the case of the projective plane, because the projective plane has edges of size root n and has n of them. So if it's not too close to one of these extremal examples, then the chromatic index is slightly better than what the conjecture says. But I won't really say much more about this result. But in fact, we actually need this result to prove our main theorem. So for the remainder of the talk, I will tell you a bit about how we prove the result. To start off with, let me just give you an overview, a high-level overview of how the proof goes. You can roughly split the proof into two phases. In the first phase, we start with the large edges, which is edges of size at least some absolute constant, like 1,000,000 or something. And I'll talk more about this later, but at this point, I'll just point out that here it's actually useful to consider the line graph. And then the second phase is to move on to the small edges and color them with the same set of colors in a way that's compatible with the coloring from the first phase. And there we use the nibble method, which is what's used to prove the Pippinger-Spencer theorem. And we kind of combine it with absorption techniques to reduce the problem to edge coloring graph. In particular, we would like to use Vissing's theorem. And so the upshot of all this at this point is that in both phases, it's really important that we reduce the problem to a graph coloring problem. We go from hypergraphs to graphs, but you need to do it in the right way because you could just take the line graph and say, oh, I have a graph coloring problem already. But that is in general not manageable. For the case when the edges are all large, it turns out that it is manageable. And for the case when the edges are small, it turns out that it's best to stay in the edge coloring regime. So now I'll tell you about phase two. So let's just, I'm going to go kind of in reverse order from the proof. And let's suppose that we have a hypergraph where the edge sizes are bounded. So forget about phase one and forget about avoiding conflicts with the colorings for the large edges. We just want to color this hypergraph with bounded edge sizes. And this would already be a new result. And let's just assume actually that edges have size either 2 or 3, because it simplifies things a bit. And it already captures, I think, it captures our strategy pretty well already with edges having size 2 or 3. So first, before we start, note that if there's a pair of vertices in the hypergraph that's not contained in an edge, then we can always just add an edge. So for example, in this bottom right picture, if say this pair of vertices wasn't in an edge, we could just put the edge in and we only made the problem more difficult, but we still have a hypergraph satisfying the hypotheses. So having done this, since edges have size 2 or 3 and the hypergraph is linear, every vertex will have degree between n/2 and n, roughly. A vertex on one end of the spectrum, a vertex that's contained in exclusively triangles will have degree n-1/2. And on the other end of the spectrum, a vertex incident to only graph edges will have degree n-1. And so this low degree vertex, on the one hand, it has more flexibility in that we have n colors to work with. And to color at least this local part of the graph, we only need n/2, essentially. The downside is that the size 3 edges are more difficult to work with because, like I said, going from graphs to hypergraphs, things get a lot more complicated. So the upside of the high degree vertices is that they're more graph-like. But the downside, again, is that we need more colors to color vertices of high degree locally. But this dichotomy, I think, is important to keep in mind as we go through the proof strategy. So now, okay, before telling you about the proof, as a warm-up, I'm going to give you what I call a dream proof. It's something that's not going to work, but I think it captures our strategy fairly well. As I said, our objective is to reduce the problem to edge coloring a graph. And to do that, we're going to just split our set of colors in half and use the first half of the colors to get rid of the edges of size 3. So we're going to color the edges of size 3. But we can't just ignore the vertices of high degree because every color needs to appear there as well. So what we'll do is, not only will we color the size 3 edges, we will also try to color at least half of the graph edges containing every vertex. So in this picture below, I've colored all of the size 3 edges containing this vertex, and I've colored half the graph edges containing this vertex. And if you could accomplish this, then the uncolored edges would form a graph. So not just a hypergraph, a graph, and the maximum degree would be less than n minus k. So in this case below, the uncolored graph would have max degree 4, which is strictly less than n minus k. And then you would be done, because you could just apply Ising's theorem to the uncolored graph. Half the colors come from this dream-proof strategy, and the other half comes from Ising's theorem. But like I said, this is too much to hope for. Like I said, there's no, well, the size 3 edges are too difficult to work with. But we haven't used the flexibility of the colors on the low degree vertices yet. So what we'll do is try to massage this dream-proof strategy in such a way that we can kind of approximate it with a random approach. So to do that, we'll use, instead of using exactly n/2 colors, we'll use a bit more than n/2 colors. We'll allow ourselves an extra gamma n colors, where gamma is some small constant. And we'll, again, color all the size 3 edges. But now for each vertex, we have a slightly more relaxed condition that we color nearly half of the graph edges containing it, rather than exactly at least half. In order to compensate for that, we need to do something a bit more for the vertices that have really high degree. So we let U be the vertices that have degree really close to n, at least 1 minus epsilon n, where epsilon is some small constant. Something like 1/100 should work. And there we need to color, there we'll try to ensure that every color class covers these really high degree vertices. So if we can accomplish these 3 bullet points with this many colors, then we will still have this star property from the dream-proof strategy. We'll still have that the remaining uncolored edges have max degree at most n minus k, and we'll still be able to finish with Ising's theorem. So let me explain that a little more precisely, and in particular, describe how we can use the probabilistic method to find such a coloring. The first thing that we would do is put each graph edge in a reservoir independently with probability of half. So basically, we would just flip a coin for every edge of size 2, and if it's heads, we put it in the reservoir, and if it's tails, we don't. And it's easy to see that with high probability, roughly half of the graph edges containing every vertex would put in the reservoir, and roughly half will remain. And in particular, the maximum degree of the non-reservoir hypergraph will be just a bit more than n/2. So at that point, we can apply the Pippinger-Spencer theorem to the non-reserved graph to find a proper edge coloring with at most n/2 plus gamma n colors, which is what we had from the previous slide. And in doing so, we would accomplish 2 out of those 3 goals. The first goal is that we have colored all of the size 3 edges, because the size 3 edges were not in the reservoir. And nearly half of the graph edges containing every vertex will be colored, because essentially half of the graph edges containing each vertex are not in the reservoir. But we still need to accomplish that third goal, which is that every color class covers U, that we have perfect coverage. And so this is where absorption comes into the picture, because the Pippinger-Spencer theorem is proved via the Nibble method. And so to get this extra property, we kind of unpack the Pippinger-Spencer theorem, apply the Nibble method, and kind of boost it with the absorption technique to get the third bullet point, basically. And the idea is you take a coloring from Pippinger-Spencer, and you want to use these reservoir edges to kind of augment your color classes. Your color classes are matchings, and you can add in some of the reservoir edges to those matchings so that they cover the set U. And if you can do that, then you can see that the vertices in U have leftover degree at most this, because initially they had degree at most n-1, and at least k edges containing them are colored, and so they have degree in the uncolored graph less than n-k. And the vertices not in U have leftover degree at most this, because their degree in the original graph was at most 1 minus epsilon n, and just only a bit more than half were even in the reservoir. And thus, we still have this property that the uncolored edges of our graph max degree at most this, and so we can apply Vizing's theorem as before. Okay. Unfortunately, I've lied to you again. This doesn't quite work, but this is really close to the truth. In particular, if the graph is, for example, Kn, one of the extremal examples when n is odd, then this set U of high degree vertices is just the set of all the vertices. And if we were to find a coloring that has this perfect coverage property, then every color class would be a perfect matching, but no perfect matching exists. So instead, we find a coloring that's like not quite perfect coverage, but nearly perfect coverage. In particular, every color class is basically as close to covering U as possible. It might miss one vertex, and every vertex of U is covered by all but one color class. And so if you run this back through the proof, you can truthfully find, using this nibble and absorption technique, such a coloring of this H prime containing H minus R that has nearly perfect coverage. And you can kind of adjust the values a bit, and basically you just need one extra color, which corresponds from going from perfect to nearly perfect coverage. So there's actually a fairly short proof that the EFL conjecture is true if you allow yourself one more color when the edge sizes are bounded, using this strategy. And we need additional ideas to get rid of this one extra color that I won't go into today, but it's somewhat painful how much extra work it is to get rid of the one color. So to wrap up this section on the small edges, let me explain to you how we actually do this nibble and absorption thing, because at this point it might seem a bit magical. So recall the setup is that U is the set of high degree vertices, and R is this random reservoir. And we apply the nibble method, which I'll briefly describe. So we want to construct a coloring of the hypergraph, and we'll do it by finding the color classes one by one. And each color class is a matching. So the very first thing we do is select some edges to be colored blue. Say we're going to start with the color blue, and so we select some edges randomly. And if two edges overlap at a vertex, then we can't color them both blue, so we just ignore them. But the remaining edges, we can indeed assign blue because they form a matching. And we repeat this process where we select additional edges randomly. And again, if these overlap, then we forget about them, but we keep what remains. And each of these stages is called a bite. And since we're repeating it multiple times, we're kind of nibbling at the graph. And so as we go, say that everything inside this blue region is covered by an edge that we've assigned the color blue. And keep going until you reach a point where almost all of the vertices have been covered by an edge colored blue. The magic of the nibble method is that this actually works. It's not clear at all that this random process will construct a large matching, but it does indeed work. In fact, these vertices in the white area here that are uncovered, roughly they look like they were selected independently from each other with probability gamma, where gamma is some small constant. And this fact actually kind of allows the nibble to continue. But it's also something that we will use in the proof. So at this point, we use the absorption method. We've covered almost all the vertices of the graph with the blue color class, but we want to make sure that the blue color class covers U. And we do this in two cases. If U is small, then we use these crossing edges. So we look at the vertices inside U, and we find edges in the reservoir that go from U to outside of U. And we color them blue. And if U is big, then we find these edges kind of internally inside U. And the proof that this works, well, to see that this works, consider a simplified version where just suppose, for simplicity, every vertex in U has full degree. Every vertex has degree n-1. And suppose that the vertices that have been left uncovered by this large matching were actually chosen independently with probability gamma. And so it's actually kind of it's a fairly easy exercise to show that in this setting, you have this graph where the vertices have degree n-1. You randomly select edges with the probability 1/2 to be an R, and then you randomly select vertices with probability gamma, and you want to show that it has a matching that either saturates the U vertices with edges crossing or on the inside. It's not that difficult to show. And so our proof is a bit more technical because we need to, we don't have this independence exactly, but we have it approximately. But the idea is essentially the same. Okay, so that was a lot of work just to construct one color class. And now we need to repeat this process. We need to use K colors, which was more than n/2. But that part is just the same argument. So now let's say the second color class is the color red. So we again try to construct a large matching, and we assign the colors of this large matching red. We look at the vertices that have been uncovered, and then we apply this absorption argument again to kind of patch up what remains. The reason it's called absorption is because these vertices of U are kind of being absorbed into the color class at each stage. Okay, so now we repeat this process n/2 times, and trust me that even by the last stage of the process, you can still find these matchings in the reservoir. Okay. That's it for the small edges. Now let me talk about the large edges. So going back, phase 2 was for the small edges. Phase 1 of the proof is actually how we start. We color the large edges first. It's fairly trivial to show that in a linear hypergraph, an edge E has at most this many edges that have at least the same size to intersect it. So the numerator here counts the number of pairs of vertices where one vertex is in E and the other vertex is not in E. And each edge intersecting E will have, it kind of consumes this many of those pairs. So this is an upper bound on the number of edges of size at least E intersecting E. And since R is a really large, since R is a really large number, this is close to N. It's basically N plus N/R. At this point, it's useful to consider the line graph. In particular, imagine that the vertices of the line graph, which are edges of the hypergraph, have been laid out on this line here. And we'll consider them to be ordered, where the vertices on the left come before ones on the right. And if we order them by the size, as I alluded to earlier in the talk, then this trivial fact at the start will imply that the forward degree is always n plus little of n. So the large edges are on the left, the small edges are on the right. And if we color the edges from left to right greedily, we'll use at most this many colors. And so our goal is to color it with only n colors. We need to figure out how to get rid of this extra little bit of colors. Ideally, we would be able to find an ordering where the forward degree is not just n plus little o of n, but it's actually n. And our strategy will be to try to find such an ordering in the following way. It's quite simple. Start with this size monotone decreasing ordering, and let E be the last edge that has forward degree that's too large. That's forward degree at least n. So all of the edges that come after E, they're good. They have forward degree less than n. If there's a neighbor of E that has at most n edges that come before E, then we can just move F to become after E in the ordering. And this will constitute progress because F will then have forward degree at most n. And so the number of good edges at the end will have increased by 1. And then additionally, E's forward degree will have dropped by 1. And so we just try to repeat this process for as long as we can. And if it finishes, meaning that we've shuffled things around and it goes all the way to the left, then every edge will have forward degree less than n, and we can just color greedily, as I said. If the process fails, if it gets stuck, then we actually have found something that's highly structured. So for example, if it gets stuck at E, then E will have many neighbors that all have many neighbors close to E. So we have this structure. And the idea of the proof is to exploit this structure in such a way that we can just, well, to use the structure to color it, basically. Okay, so this is a little bit more explicit about what that structure is. So let's say W is that highly structured set that we found from getting stuck. The two important structural properties are that almost all of the pairs of vertices are covered by an edge of W. And so since the hypergraph is linear and every pair of vertices is contained at most one edge, this really limits what can happen outside of W. So almost all of the pairs of vertices are covered by W. And the other property is that the edges all have size, well, the edges all have roughly the same size. And I'll use this zeta to kind of parameterize that. So this is still informal at this point, but all of the edges of W have size roughly 1 minus zeta times root n. And so still the vertices of the line graph are laid out in this line. This is W in the middle. Because of the way that we did this reordering process, the vertices to the right of W have forward degree less than n. These were the good vertices. And because we started with this size monotone decreasing ordering, all of the vertices in the line graph to the left of W have size at least that of any edge in W. So in particular, at least 1 minus zeta times root n. And we will consider two cases based on what zeta is. If zeta is small, then this is kind of the extremal case, because W will resemble the projective plane. Because if zeta is small, then all of the edges have size close to root n. And delta is small, so W covers almost all of the pairs of vertices. So W looks like the projective plane because it's roughly n edges of size root n. In this case, our strategy to color is to find this many pairs of disjoint edges in H1 and W. There's not that many more than n edges in this segment of the hypergraph. And we can just find these disjoint edges and assign the edges of those pairs the same color, and assign the remaining edges their own distinct color. So all of the color classes are matchings of size either 1 or 2 in H1 and W. And this is maybe a 3-page argument. But once we've done that, we can extend the coloring to H2 greedily. And so we've colored the hypergraph within colors, and that's good. The other case is when zeta is large. And in this case, First we show that the line graph of W has maximum degree close to n, which follows from the linearity from using an argument from the previous slide. And we additionally show that W is locally sparse, which means that considering the line graph, the neighborhood of every vertex is missing roughly a zeta proportion of the possible edges. And this again just follows from the linearity of the hypergraph. Once we know that, we can apply this theorem of Molly and Reed that says that we can color W with some number of colors that's bounded away from n, some constant times zeta n. And we'll do so randomly using the probabilistic method again. So that's just to color W, but we still need to color H1. But for that, we can apply the same kind of reordering ideas to H1. And so ultimately what we do is we color H1 greedily in the ordering with a very small set of colors. And then we color W with a disjoint set of colors so that together we've used the most n colors. And then we can extend the coloring to H2 greedily. And so that's the overview of the proof in the large edge case. Okay, so to wrap up, I want to just share some open problems with you. There are a lot of open problems about coloring hypergraphs, but I'll just focus on a couple that are related to the EFL conjecture. And in fact, all of these are generalizations of the EFL conjecture if true. I think this one's a beautiful conjecture, although at first this number might look a bit weird. If true, this conjecture of Bursch, Ferretti, and Manuel would give a stronger bound on the chromatic index than what Erdős, Faber, Lovász conjecture gives you. A good way to think about this quantity is to think about the shadow of a hypergraph. So if this is the hypergraph, we obtain the shadow by replacing each hyperedge with a complete graph. And this quantity here is just the maximum degree of the shadow graph plus 1. And since every graph is the shadow of itself, this conjecture, if true, would imply the EFL conjecture, but it would also imply Vissing's theorem. So it would be a common generalization of both. Because for graphs, this quantity is what Vissing's theorem gives you. So I think that's nice. Another natural generalization of the EFL conjecture is just to ask if it holds for list coloring. So can you replace the chromatic index with the list chromatic index? So in particular, if each edge has a list of colors of size at least n, then can you find a proper edge coloring such that every edge receives a color from the list? The case when every edge has the same set of n colors is equivalent to the EFL conjecture. And the last thing is that maybe there's a common generalization of both of these. Maybe there's a list setting of, maybe there's a list coloring version of the Bursch, Ferretti, Manuel conjecture. But this would be maybe too optimistic. It'd be really great if it's true, because not only would it give you a common generalization of EFL and the Bursch, Ferretti, Manuel conjecture, it would also imply a weak version of the list coloring conjecture, because it's not even known for graphs that they have list chromatic index at most, their max degree plus 1. Anyways, that's all I wanted to say. So thank you everyone for listening.
Oh, thank you, Tom. It's a very nice talk. So any questions for Tom?
I was wondering if you could tell us a bit more in the conjectures known to hold the first conjecture there.
Pardon?
When's the first conjecture? What are some results first conjecture, some partial results?
For the Bursch, Ferretti, Manuel one? So some analog of Kahn's result holds. It hasn't actually been written down, but Kahn's proof just works. So 1 plus little of 1 times this. Otherwise, not much. There's not much to say.
And I mean, it's a nice list local version.
a WISP local version of this? Yeah, that's a good question. I'll have to think about that one. Yeah, the asymptotic list version. So I guess before you get a WISP local version, you need a list version. The list version of this, where it's list chromatic index and 1 plus middle of 1, that also holds. For that, you need, it's essentially the same proof as Kahn's proof again, but you need, I don't know, when Kahn proved in 92 the asymptotic version of the EFL, he didn't quite have a full list coloring version of Pippinger-Spencer. So he wasn't at the time able to get the list version of EFL. But later, he proved that Pippinger-Spencer actually holds for the list chromatic index. And so if you combine that with his proof, then yeah, you can get asymptotic list versus Ready manual. So yeah, maybe asymptotic local list versus Ready manual. I don't know. That's interesting.
Other questions? So Tom, in the phase where the final phase where you use the absorption, I'm just wondering if it's possible to describe what the absorber look like, and also how big the absorber is.
Well, it's kind of it's a very uncomplicated application of absorption, because the absorber is really just the reservoir. The reservoir is just obtained by reserving the graph edges with probability of half. So since these vertices in U have high degree, it's just kind of a graph with degrees like n/2. And yeah, and so you just apply Hall's theorem to the graph induced by the reservoir. So there's not really any additional structure that we need. Yeah.
So those reservoir, you don't color them. So those are are they the set of edges that you colored in the end, or?
Well, it depends what you mean by end. The end of there's lots of phases. Sorry?
The end of the process. Is that is it the covered after the nibbles?
Well, so let's just say we apply n/2 different nibbles to construct n/2 color classes. Then we apply n/2 absorption steps as well. We alternate nibble absorption, nibble absorption. And so when we do absorption after the nibble, we are essentially picking some edges out of the reservoir to color.
I see.
Yeah, so we kind of debated whether or not to call it absorption, but I'm using the term absorption to.
I see. So it's just uncolored edges in some sense, and then you like swapping the colors or something like that. Or maybe I'm not really using the right terminology. So like swapping the edges in the matching and edges in the U or something like that.
Yeah, well, I guess there's no swapping. We're saving the reservoir edges kind of for last, but we're also pulling out some of them to give a color to early on.
Okay, yeah. I think I think it might be quite different from what I thought, but
yeah. So maybe I should clarify like why we use the term absorption. At a very high level, I think of absorption as some process by which you can take some kind of nearly spanning structure and making it spanning. And in this case, the nearly spanning structure is the nearly perfect matching that you get by nibble.
Yeah.
And you make it, well, Yeah, you make it spanning by adding the reservoir edges so that it spans you. It doesn't necessarily span the whole graph, but it at least spans you.
I see. I see. So
Does that make sense?
yeah, it makes sense. It's just you just have to add edges. I thought that maybe like in the graph case, I thought maybe it's not easy to find a spanning about perfect matching, but then the remaining structure you have to get it by augmenting the path in some way. But in your case, you just have to add edges to make it spanning, right?
Yeah, exactly.
Okay.
The extra edges are actually useful.
Okay.
If we didn't add the extra graph edges, then we might not be able to find the spanning matching, like if it was a Steiner triple system or something. But
okay, thank you. Other questions?
Yeah, so this is probably asking too much, but I'm wondering if there could maybe possibly be some kind of perfect graph type theorem. So you know that if you have a line graph and every induced subgraph of it has this Feising's bound being on the lower side equal to delta, that this happens if and only if you don't have an odd cycle of length larger than 3. And so here you have like 3 examples of graphs, the projective planes and the cliques and
yeah.
the third thing. And so I'm wondering if like maybe possibly these could in some sense be the only tight examples. Say if you're closed somehow.
Yeah, that's an interesting conjecture. That's an interesting question, and I can definitely say something about that, but I need to think. I mean, something that's related, I was wondering, is if line graphs of linear hypergraphs are chi-bounded. Does that sound kind of similar to your question? Like, forget about perfect for a second, just even chi-bounded.
Just
so
trying to show something.
Can you bound it by some function of the clique number of the line graph? But this is not possible. That's false. And the reason is that every graph is the line graph of a linear hypergraph. And that's not obvious at all, but there's a way to show that, well, if I give you a graph, I can construct a linear hypergraph such that the graph you gave me is its line graph. And so, where am I going with this? I lost my train of thought. So
Yeah, I guess you'd want to restrict to hypergraphs that have this property at the end. I don't know.
yeah, I mean, in some sort of sense, the Burge-Freddie-Manuel conjecture is along the lines of what you're thinking, because I think of it like, could you do even better than this and replace this quantity with the clique number of the line graph or something? But it's not possible. And sorry, I can't think of exactly why at the moment.
Thank you. That answers the question.
Okay.
Well, maybe we can leave for sorry to the virtual grad house for more discussions. So let's unmute ourselves and thank Tom for the nice talk.